Okay, so with number 8, we've got another one of these questions that's got a trip with more than one part in it. Okay, so it makes a 60-kilometer trip with an average velocity of 40 kilometers per hour in a direction due north. All right, the trip consists of 3 parts. The car moves at a constant velocity of 25 kilometers per hour due north for the first 15 kilometers, 62 kilometers per hour due north for the next 32 kilometers. Okay, draw a position time graph of this situation, and B, with what velocity does the car travel for the last 13 kilometers? Well, if we don't know the velocity in the last 13 kilometers, it's going to be pretty hard really for us to draw the graph initially. I mean, we could do it, but it probably makes more sense to find out the information we need and then draw the graph. Okay, so here's what we know first off. They told us information about the total trip. We know the whole trip is 60 kilometers. Okay, and that is that it is north as well, okay, because they told us that. And they told us the average velocity over the whole trip was 40 kilometers per hour. Okay, what we don't know is how long the whole trip took, but could we find it? Right, we have D and we have V, so we could find time. We probably want that. Okay, we're going to want the total time for the whole trip. Okay, so let's find that. So it'll be 60 divided by 40, okay, D over V, which should be 1.5 hours. Everybody with me so far? All right, so that's just the first part of our givens. Okay, the first section or leg of this trip, okay, the car moves at a velocity of 25 kilometers per hour, and that's also north. Okay, for the first 15 kilometers. And in part 2, we move at 62 kilometers per hour for 32 kilometers. And that's also north. And then they tell us that in part 3 is 13 kilometers long. All right, so what they want to know is, what's the velocity in part 3? If I want to find V for part 3, what else do I need to know about part 3? Time. Yeah, I've got to have the time. Now, I know how long the whole trip takes, and I have D and V for both of the other parts. Can I find the time for the other 2 parts? Okay, if I know the time for 2 out of 3, and I know what all 3 add up to, can I find the remaining time? All right, so that's the route I've got to take here. All right, so time is going to equal, again, D over V. So that's going to be 25 over 50. Oh, sorry, 15 over 25. Sorry. Okay, so it's 0.6 hours for this one. Got to do the same thing here. Time will equal D over V, so that'll be 32 over 62. So we got 0.516 hours there. Would I keep all those decimals? Yes, I'm just not going to write them all down. I am going to keep them. They're in the calculator, but I'm not going to write them all down. Okay, the whole trip takes 1.5 hours. I know how long these 2 parts take, so the time for part 3 is going to be 1.5 minus 0.6 minus 0.516. Okay, that'll give me the time for that part. So we'll go. Right, so our remaining time is 0.38. I'm going to round to 4, but 0.384. But okay, I'm going to keep all those decimals when I do my later calculation. All right, so the last part takes 0.384 hours. Now I can figure out what my velocity is during that part. So it'll be 13, the displacement, divided by the time, 0.384, but I'll use all the decimals there. so the last part of my trip is 33.87 because I think I made this answer with a rounded off number. Okay, 33 point, actually, and we only have two significant figures here, so that'll be 34 kilometers per hour. Okay, everybody follow what I did there? All right, all I made you do was manipulate v equals d over t about 5 times in one question, which was my plan. Okay, just to make you practice manipulating v equals d over t a little bit. Now, the next part of this is that we were supposed to draw a position versus time graph of this trip. At no point in this trip do we go south, right? Everything is north in this trip. All right, so we'll have our position here on the y-axis, and that'll be in kilometers. And we'll have our time down here, and that'll be in hours. Okay. I'm going to make each one of those worth 0.1 hours, okay? And that way we can kind of make at least a rough graph. Obviously, it was never intended for you to draw it perfectly to scale. Okay, so that'll allow me to get the whole trip on the graph. Everybody okay with that? Okay, in the first part of the trip, sorry, we gotta put the axis on here too. I'm gonna make each one of those worth 10 kilometers. Okay, in the first part of the trip, it says we traveled 15 kilometers north, and that took 0.6 hours. So I'm gonna go to 0.6 up to about where that one is. And we did that at a constant velocity of 25 kilometers per hour. So really what I would do is this. That would be the first part of my graph. Okay. Second part of my graph, we go 32 kilometers in 0.516 hours. So that'll be about here or so. And I need to go another 32 kilometers beyond 15. So up to 47, so somewhere in that area, because again, I don't have a good scale here. Okay, and then our last point will be at 60 at 1.5. Okay. So if I'm just doing like a connect the dots graph, that's what it would look like. Okay. If I'm doing a proper line graph, how many lines should I have on there? Just one. Okay, I should have just one line on there. Okay, and just draw it like this. Okay, probably something like that, right? And that would, the slope of that line would represent my average velocity over the whole trip and would have a value of about 40 kilometers per hour. Everybody all right with that? Okay, is that ringing a bell a little bit from Science 10? Being able to draw those out. Obviously, we're not going to draw very many graphs by hand because that's really old school. Okay, we can do them on the computer, on calculators, whatever. There's no point in drawing them out by hand. It's painstaking, and it's not nearly as accurate either. All right, what I need you guys to do is take out your notes for lesson 7. I'm going to go over all the stuff to do with graphing. So hopefully most of this stuff is going to be familiar from Science 10. All right, so basically today we're just going to go over position versus time and velocity versus time graphs. Those will be the most important graphs for this unit, okay? And their review, or they should be, okay, from Science 10. So we need to understand what kind of information can be read from those two types of graphs, what kind of information can be calculated from those two graphs, okay, and a little bit of review of y equals mx plus b. All right, we're going to have to use that quite a bit here as well, especially this week when we do our first lab and we're running some carts down the, well, actually just on the floor in the room here, okay, and using some electronic measuring devices rather than having to put yellow sticky notes down on the floor where they are, because that's not very accurate. Okay. So understand that graphs and equations from kinematics show the same information in different ways. Almost all of the formulas that we use in this course are somehow derived from a graph. Okay, especially the ones here in kinematics. And that lastly, learn that kinematics equations are, again, derived from graphing. So we'll start out with position versus time graphs. Okay, position versus time graphs tell me where an object is at various points in time. Okay, what its position is as a function of time. That can allow me to calculate a few things. If I know where an object is and where it has been, can I find out how far it has traveled? Okay, so I can calculate distance. If I can calculate distance, could I also calculate its vector equivalent? Could I calculate displacement from a position time graph? I sure hope so, because last week we talked about how displacement is final position minus initial position, and I'm pretty sure those two things would be on this graph somewhere. Okay. If this graph not only shows position but also shows time, could I calculate velocity off of this graph? Okay. Should be able to, because velocity is the change in position over time. Okay. In other words, displacement over time. Right. So that we should be able to calculate those things from this graph. Okay, looking at this graph. Okay, in this first section of the graph here, the line is straight. Okay, it says there on the graph that it's traveling at a constant velocity of 180 kilometers per hour. How do I know that a straight line on this graph is equivalent to traveling at a constant velocity? Because that's something I should just be able to recognize when I look at the graph. I say recognize, not memorize. Okay, should just be able to recognize that. Okay, on any graph, okay, doesn't matter what the graph is, if I have a straight line, it's telling me that whatever's on the y goes up at a specific rate with x. Agreed? Okay. If it wasn't straight, then the rate would change. Okay. In this case, on a position versus time graph, it's saying that I change my position by the same amount every time interval. And if I'm doing that, then I must be traveling at a constant velocity of however many meters per second or kilometers per hour. Okay? Because every time interval, I change my position by the same amount in the same direction. Everybody okay with that? Okay, that's what a straight line means. Now here, we see that the line is no longer straight. Okay? It's curving towards flat. And on the graph there on the diagram, it says that it is decelerating, not a term we use in physics. Okay? We use the term, it's accelerating. It's just accelerating, backwards or negatively. Okay? We don't use accelerate and decelerate. Accelerate means change in velocity. Doesn't matter whether it's positive or negative. All right, so this thing is accelerating in a negative direction, okay? And it's no longer a straight line, which means that the amount of position covered every second is no longer the same. Okay, it's getting flatter and flatter and flatter. Okay, if it's getting flatter, okay, it's slowing down. Because on this graph, if the line is flat, what is the object not doing? It's not moving. Okay, if the line on a position versus time graph is flat, then the position isn't changing. In other words, the object is staying still. Okay, kind of following me there? Okay? Again, we don't want to memorize that. We want to be able to look at a graph and say, well, it's position here, and the position's not changing. When position's not changing, something's not moving. Okay, those are the, because while in Science 10 you could memorize all that stuff for the graphs, in Physics 20 we deal with a lot more graphs, and in Physics 30 it's like 60 graphs. Okay, it's like 60 different graphs that you'll encounter in Physics 30. Okay, you can't possibly memorize what you can get and read and everything off of every one of those graphs. Okay, it's more important to be able to read a graph as opposed to memorize what's on it. Okay. All right, so this line here has a specific slope, and that specific slope represents the velocity of the object. When the line is a curve, the slope of the line is constantly changing. Okay? And a change in velocity is acceleration. Okay? So this object's slowing down because the slope of the line is getting lower and lower and lower. Remember to turn that back on. Okay, so I'm going to extend this line down. I don't want that one though. Okay, so on this line here, okay, this would be B. Okay, this line, I could be using this point or that point. I'm going to say I'm using this point. Okay, this would be Y. This would be X. Everybody all right with that? Okay. So if I want to calculate the slope using this formula, I've got to isolate M. Think back to our rules of algebra here. Okay, if I want to move something, I do the opposite. What I do to one side, I do to the other, and I move what's not attached to what I'm looking for first. So what should I move first if I want to get M by itself? B. Okay, B is not attached to M. X is. All right, so I'm going to subtract B from both sides. So I'll have Y minus B equals M times X. Okay, divide both sides by X, and I've got my formula for the slope. Y minus B divided by X, which is that. Okay, that's where rise over run comes from. I'm taking Y2 minus Y1 over X2 minus X1. It just happens that X1 is 0. Okay, so it's same formula, right? Same formula, just once I have slope, I can do a lot more with it with Y equals mx plus b. Okay. How many people learned Y equals mx plus b last year? Okay. So position versus time graph. What is happening in part A of this graph? Okay, it's moving at a constant speed. Is it accelerating? You said both. No. Okay, but it is moving at a constant speed. We always want to say that, right? Because we see a line going up, it just feels like accelerates the right answer. Okay, but it is moving at a constant speed. Okay, and it's moving at a constant speed in a forward direction. Okay, everybody with me there? How do I know it's moving forwards? Yeah, it's becoming more positive. I would assume positive is forwards. Okay, what's going on in part B? It stopped. Its position stays at 6 meters for 4 seconds. Okay, it's not moving. In part C, what is it doing? Is it accelerating? Okay, no, you're right. I said not use decelerate. But is this line showing a change in velocity or a change in position? Okay, showing a change in position, right? This is a position versus time graph. Okay, this would be curved if it was accelerating. Okay, so this object is just moving backwards at a constant velocity. Okay, constant velocity. Then in part D, the object is standing still. All right, and then in part E, it's moving forwards at a constant velocity. Same with part F, moving forwards at a constant velocity. E or F faster? Which one's faster, E or F? Okay, how do we know E is faster? It's steeper, right? Okay, E is steeper, so the rate of change of position is much greater in part E, okay, than it would be here. Everybody follow? I want you guys to try this calculation. I want you to calculate for me the average velocity over the whole trip. Okay, should be done. Why should you already be done? Because it's 0. Okay? How do I know it's 0? Exactly. The starting position is 0. The ending position is also 0, which means the displacement of this object is 0. Therefore, the velocity has to be 0 as well. Okay. Sometimes questions are like that. Okay. Like on a multiple choice question on an exam, that's one of the ones that helps people get ahead or causes them to get really far behind. Okay. It's one or the other. People either do a whole bunch of calculating to prove something that should take 1 second, or they recognize right away that this should only take 1 second. Everybody with me there? Okay. Those are those questions that eat up time if you're not well prepared. All right, now I want you, this one will actually require you to do a little calculating. I want you to calculate the total distance traveled in this graph. Okay, the total distance traveled, not the displacement, we know that's 0. The total distance traveled. I'm gonna give you a couple minutes on that. All right, so in order to calculate the total distance traveled, I need to figure out how far it goes in each section of the graph. So there's 2 sections of the graph I don't have to bother with. What 2 sections are those? Yeah, B and D. It doesn't go anywhere in those sections, so I don't even have to worry about those. All right, in part A, it goes from a position of 0 meters to a position of 6 meters. All right, so I know that at least in this part, it goes 6 meters. Then in part C, it goes from positive 6 to negative 10. So that's going to be 16 meters. Again, this is scalar now, right? I'm dealing with distance, so it doesn't matter that that 16 is negative. Okay, it's for scalar, it doesn't matter. All right, and then between E and F, I've got to go from negative 10 back to 0, right? So I'm just going to summarize those two as being 10 meters. Everyone all right with that? We could have done them one at a time, but it was just as easy to do it that way. All right, so we got 6 plus 16 is 22, plus 10 more. The total distance traveled is 32 meters. What's the average speed? Not 0. It's actually 18. It ends at 18. You can't see the line here, but it ends. There's a flat part there. It goes to 18. Okay, so if I want to calculate average speed, I need total distance and total time. I just calculated the total distance. Total time is 18 seconds. All right, so 1.8 meters per second. Okay, is that ringing a bell? Okay, I would have had you do one like that in my Science 10 class if you're in my Science 10 class. Questions on position versus time graph? All right. We talked the other day about if I had a trip where I traveled at one speed for a lot more of the trip than I did at another speed, and how their average would not be like adding them together and dividing by 2. Okay, that's all this top graph is showing. Okay, where you could travel at one speed and then travel at another. Your average would be steeper than one, but shallower than the other. Okay. All right. For this graph here on the bottom, what's the object doing right here in this part of the graph? Now it is accelerating, and it's accelerating which way? Negatively. Yeah, it's accelerating backwards. The line is getting steeper in a negative direction. Okay, whereas here, the object is accelerating positively because its velocity becomes less and less negative until it actually becomes. Oh, no, it's not here. It becomes 0. Right? Doesn't that line get flat? right? Flat line says position is not changing. So this is showing an object slowing down and coming to a stop. Okay. Now over here, it's showing it doing what? Accelerating, right? Accelerating positively, right? It's trying to move back toward a positive position in that part of the graph, right? Those are things we got to be able to recognize when looking at a graph. Okay, one thing you're basically never going to be asked to do because it involves you having to draw on a graph and everybody's answer would be different, okay? But that you still need to understand is how can I calculate the velocity of an object while it's accelerating? Because this graph is showing a whole bunch of accelerations, okay? But a question might ask, how fast is the object going at time 7 seconds? Okay, well, I can't really tell that because according to this graph, the object's velocity is changing. Okay, I don't know how fast it's going at time 7 seconds. All I know is that it's changing all the time. Now, the other thing we know though is that on a position versus time graph, the slope of the line is equal to velocity. Now, here's what you have to understand about a curve. I'm going to teach you the only thing I understood in university calculus. Unfortunately, it was the first day. And after that, I understood nothing. Right? I still passed the class, but I memorized all the examples in the textbook and wrote them down on the final exam. I got part marks for method. Hey, I was in a class full of really not gifted people, and they didn't figure out that if they did that, they could pass. So it wasn't that I knew anything about calculus. It was just that I was smarter than most of the people in the class. It's called the curve. You get graded on the curve. Yeah, that time I surfed the curve. They got crushed by the wave that day. Okay, so if I understand that the slope of a line on this graph is equal to velocity, and I understand that a curve is really an infinitely large number of infinitely small straight lines, then I should be able to calculate the slope of the really small straight line that exists right here at time 7 seconds. Agreed? I mean, it's a straight line. It's just really short. Can I make it longer? Yeah, if I draw a tangent. Right? So I could draw a tangent line that is going to touch the curve at that point. And a tangent line would then be parallel to the curve at that point. So the slope of my tangent would be the velocity at that point. Okay? Again, it's not something I'm ever going to ask you to do because if I did, I would have to have on a key a wide range of acceptable answers because everybody's line would be just a little bit different. Right? There's no way we would all draw exactly the same tangent line on a graph, okay, for that curve, which is why we basically don't do it. All right. So right here, the object is accelerating. Okay, what's it doing kind of through this part B here? Okay, what's going on this part of the graph here? Because we know here it accelerated, but once it kind of got to this point here, it started doing something else. What does it look like happened on this graph? Yeah, it started accelerating the other way. It started accelerating the other way right here. So before it could accelerate negatively, start moving negatively, it had to slow down. Agreed? Is that what this part of the graph is showing? Right? I mean, if I do this whole thing about drawing a tangent line, could I figure out how fast it's going right here at point B? Okay, there's my line that's tangent to that point. What's the slope of that line? 0. Okay, so in other words, right there at point B, the object's actually not moving. This is a graph of this. That's going to mean nothing when you listen to the podcast. I just threw a marker in the air, okay, and then caught it. So what's happening here in this part is the part where I'm throwing the marker. I'm accelerating it upward, okay? Once we get to about here, it's left my hand. And now the only thing acting on it is What's pulling it back? Gravity, right? Like it's left my hand. Now gravity is trying to bring it back down. So gravity slows it down till it gets to its maximum height, where it changes direction and then starts accelerating back down to the ground. Notice that both sides of this are identical. They're identical because it's gravity doing the accelerating on both sides. Okay, and then this part here, where we see it getting flat again, would be where I catch the marker. Right? I stop the marker, I slow it down, bring it to a stop. Everybody with me? All right, so that's kind of your review of position versus time graphs. Okay, just so everyone's kind of there. Now, I think before I get into velocity versus time graphs, we're going to do a little practice on position versus time. Okay, so on this question here, the first thing they want to know is what's the average velocity during each of the segments. Okay, so like A, B, and C here. Okay, so if I want to find average velocity, it's displacement divided by time, which is final position minus initial position over time. So in part A, the object goes from 0 to 25. So its change in position is positive 25 meters, or kilometers, sorry. Okay. And then that took 1 hour. So that's a pretty easy calculation. It's 25 kilometers per hour. Everyone okay with that one? All right. Then for part 2, or for part B here, okay, I can't even read it on there. So we go from 25 to, you guys got 33? Yeah, okay. Hard to read it on there. Okay, so 25 to 33. So we do our same thing, okay? V during part B is going to be our final position, 33 meters, minus our initial position, 25 meters. And that took 1.5 hours. Okay, so we've got 8 divided by 1.5, which should give us our positive 6.4 kilometers per hour. Something like that would be close to that anyway. Is it? Oh, sorry, it's 1.25? Oh, you're right, totally. Yeah, sorry, 2.5 is over here. Oh, that's not what I was looking to do. Okay, 6.4 kilometers per hour. Okay, and then in part C, same idea, okay? So the V for part C is going to be our final position minus our initial position. So our initial position is 33, okay? Our final position is going to be 27? Yeah. So 27 minus 33, and that takes another 1.25 hours. So we got -6 over 1.25, okay, which should give us negative 4.8 kilometers per hour. Everybody all right with that? Yeah? Okay, do I do the same thing now for the whole trip? Right? Is average velocity still total displacement divided by total time? All right, so I do exactly the same thing. That's where people usually make a mistake if they're going to make one. Okay, they've just done all this work to get these 3 numbers, so they go this one plus this one plus this one and divide by 3. Okay, do they represent equal parts of the trip? Then I can't do that. Okay, one of them is only for 1 hour, the other 2 are for 1.25. Okay, then they're not the same. So for the whole trip, our total displacement is 27 kilometers. That takes 3.5 hours, okay, and that's positive 27. Okay, so we should get 7.7 kilometers per hour, positive. Okay, ringing a bell.